I'm Tian. I'm excited to talk about R-Cubed, Record Replay Retroaction for database-backed applications. This is part of the DBOS project, a collaboration between Stanford, MIT, and many other institutions. At CIDR 2023 earlier this year, we presented our vision on how transactions make debugging easy. Now I'm here to talk about how we design and implement a practical time travel debugger for database-backed applications. In our paper, we mainly focus on distributed database-backed applications. For example, e-commerce shops and hotel reservation websites. People are increasingly deploying their apps on cloud platforms and in the distributed way. They usually implement application logic in distributed and stateless request handlers and run them as microservices or serverless functions, and then use database queries to transactionally read or write user data stored in remote databases. This design makes applications scale very well. However, distributed applications are hard to debug because they access and modify shared data across distributed and highly concurrent worker threads and servers. Our key insight is that their transaction-oriented data access pattern makes time travel uniquely practical. For example, to reproduce race conditions happened in the past. Guided by this insight, we built R-Cubed, a time travel debugging tool. As long as apps access shared data only through transactions, they can use R-Cubed to debug. R-Cubed provides always-on, low-overhead recording at transaction-level granularity. It can faithfully replay past request executions, and it's very fast. It also allows developers to modify their code and retroactively test their modified code on past events. Most importantly, R-Cubed has bolt-on support for most production databases, so we can use R-Cubed without modifying databases or application logic. Let's dive deeper into the debugging problem. We first need to understand why distributed applications are so hard to debug. Let me show you a real bug in Moodle, a popular online education platform. The subscribe user function contains two transactions. The first transaction checks if a user has subscribed to a forum. If not, it inserts a subscription to the database in a separate transaction. Here's an example trace that triggers the race condition. The first request checked the user was not subscribed and inserted a record. But the second request started before our once insert and didn't see the change. Both requests succeeded. Then a later request failed when it fetched the subscribers as it can see the duplication. The bug sounds simple, but Moodle developers struggle to reproduce this issue because error messages and stack traces only provide information for the failed request, our third request, but they are not helpful to reproduce the first two requests. We believe that developers really want time travel. Time travel in software development has two aspects. The first is replay, where you can faithfully re-execute past events. It will be very useful to debug a rare issue that only occurred in production. The second is retroaction, where you can execute new or modified code on past events. It will be very useful to test the correctness of a bug fix. There has been over 20 years of research on record and replay in computer systems. Unfortunately, existing tools are impractical for distributed applications. Application-level record and replay usually only support single-threaded execution and do not replay race conditions. Host system replay tools often require heavyweight instrumentation to track fine-grained time information on concurrent data accesses. None of the above systems support retroaction. Existing systems that support retroaction are usually single-threaded and cannot test concurrency issues. Then how we can make time travel practical? We found that distributed database-backed applications mostly use data transactions to access shared state. Given this transactional data access pattern, we can record concurrent data accesses at a transaction level granularity, making it much more practical. Then, we can reproduce past executions using the recorded transaction order and transaction interleaving pattern. Let me show you how we do this. So to use RCubed for replay, developers specify a range of requests they want to replay. RCubed first restores the database to a previous state, then allocate threads to execute application code, and add a breakpoint before each transaction. It stops at each breakpoint, waiting for the coordinator thread to decide when to execute each transaction and when to commit them. RCubed repeats step 2 and 3 until all requests are completed in the specific range. Here's a demo for replaying the Moodle trace. We first restore the database to the state immediately before the first request. Then we'll re-execute the concurrent subscribe user requests. Each runs their first transaction to check if the user is subscribed to the forum. Because these checks are interleaved, they both found no subscription. Then both requests will run their insert transactions. So the user is subscribed to the same forum twice. And we reproduce the same error. Then, based on faithful replay, RCubed allows developers to modify their code and test it on past events. RCubed preserves transaction order and interleaving patterns so developers can fairly compare retroactive execution to the original execution. RCubed retroaction allows nearly arbitrary code modifications. I'll demonstrate retroaction with Moodle bug fix, where we wrap the entire subscribe user function in one big transaction. So RCubed re-executes requests with the new code, but still following the same transaction order. Because the entire function is in one big transaction, its queries can no longer interleave. The second request no longer inserts an entry. So we don't get any error and verify the bug is fixed. So far, it sounds very simple because we assume transactions run sequentially or under serializable isolation. However, serializable isolation is often slow, so developers often would like to use a weaker isolation level for better performance, and snapshot isolation is one of the most popular ones. In snapshot isolation, each transaction sees a snapshot of the database, which contains all transactions committed before it starts. A transaction cannot see other uncommitted transactions. Therefore, transactions can run concurrently on their own snapshots without interference. This sounds great. Unfortunately, faithful replay under snapshot isolation is challenging because there may not exist a serial order. As we show here, the first and second transactions run in parallel under snapshot isolation. Both see user 1 is not subscribed to forum 2 and added duplicated entries to the database. Simply run R1 first or R2 first cannot reproduce the duplication issue under snapshot isolation. So how can we replay under snapshot isolation? Well, we only record transaction level information, including the snapshot information and transaction start order, and during replay, we reconstruct transaction snapshot that is equivalent to the one each transaction saw originally. The key idea is that we follow the start order to execute transactions. But after transaction T completes, we do not commit it, so other transactions can't see it. We only commit transaction T before the first transaction that has T in its snapshot. By controlling this, we can make sure that each transaction only sees data in its original snapshot. In our algorithm, we first obtain the recorded start order and begin transactions sequentially following the order. Next, for each transaction, before starting its execution, we commit all transactions that are visible to it to reconstruct its original snapshot. Finally, we re-execute the transaction T, but do not commit it after it's complete, because T will be committed right before the first transaction that has T in its snapshot. We formally prove the correctness of this algorithm, and please see our paper for it. Then, how do we integrate with applications? R-Cubed lightweight interceptor traces requests and transactions in production and sends it to the data recorder to enable replay and retroaction in the R-Cubed runtime integrated with the testing environment. We evaluated R-Cubed using a diverse workloads. So in the following slides, I'm going to show results for TPCC and Moodle. TPCC is the industry standard benchmark for OLTP databases, which contains complex transactions. Moodle, as we introduced, a popular online education platform. We benchmark its point read and write operations for forum subscriptions. So for more experiments on more applications, please read our paper. We implement those workloads with Postgres as the application database and Vertica as the data recorder. So we found that R-Cubed recording adds small overhead. The performance overhead is less than 25% for point queries, but the overhead is less than 0.1% for complex transactions like in TPCC. We find the main overhead is to use a separate query to get the transaction snapshot information from Postgres, which causes a 100 microsecond overhead per transaction. We also look at storage overhead. So it's about 42 to 100 bytes per request, depending on the application input sizes. So if an application serves 1,000 requests per second, we can efficiently store more than 3 months of traces in the 1 terabyte disk, which is fairly cheap. We then test the speed of replay. We execute workloads for 1 minute using different loads, and on the x-axis, you can see the increasing number of requests. The replay runtime is shown on the y-axis, and the dashed orange line represents the original execution time, 60 seconds. So we find R-Cubed can faithfully replay past requests within 0.2 to 1.4 times of the original time, mostly faster, sometimes slower. So we can be faster than the original execution because we use several optimizations such as parallelizing replay execution and commit. The main bottleneck is coordination and validating snapshots to guarantee correctness. We then retroactively execute the Moodle bug fix code over the generated traces. We find R-Cubed retroaction can always finish within the original time because we only execute transactions that have dependencies with the modified code. We have a detailed selective execution algorithm in the paper. So this is R-Cubed. The main takeaway message is that transaction-oriented data access pattern makes time travel practical and simplifies debugging for distributed applications. R-Cubed is open source. Please check our paper and code for more details. Thank you.